Our final speaker of this workshop is Matt Knepley, who's going to continue on the computational theme.
Okay, thanks, John. Thank you to the organizers for inviting me. It's an honor, and I'm going to talk sort of a second part to the talk that Dave did, except I'm going to talk about nonlinear things, and unfortunately I'm not as good at the kind of pedagogical presentation as Dave, so it won't be as tutorial, but hopefully it'll be understandable. And so I just wanted to thank the people that helped me. So Rich explained everything that I know about magma dynamics to me, unfortunately not everything he knows. And Jed helped me with the time stepping, and Toby helped me with adaptive refinement. I was going to talk about adaptive refinement, but I think, judging by how people have done on time, we will never make it there. So this is what I was going to talk about, but that's probably not going to happen. So we'll talk about nonlinear solvers, and then maybe if there's time, talk about implications of discretization. So here's why I want to talk about it. So I do find nonlinear solvers mathematically interesting and aesthetically pleasing, but maybe everyone doesn't. However, if you want to solve these equations, you have to cope with some of these nonlinearities. And it's not enough to just explicitly step them out as you might do in gas dynamics or something like that, because this is a DAE, the way that people write it down, and so I do have to solve these nonlinear equations. And the problem is that when you reach an impasse, there are few rules of thumb for proceeding forward. As you saw with Dave, we have some excellent theoretical guidance on the linear end. This excellent theoretical guidance fails us on the nonlinear end. So I kind of want to show you what the empirical things that we can do and ways that they work, and then maybe we'll have time to talk about possible theoretical avenues. I'm not sure. Okay. So why is it important? So what's important for science is making good computational decisions, right? When you decide to solve a problem, what do you want to use? And the only way to make good decisions is to be able to compare. Unfortunately, we have pretty weak frameworks for comparison. So people decide, I will discretize the problem this way, I will write this solver, this will take my entire PhD, and then it gets thrown away. And this doesn't facilitate the kind of comparison that we usually get with, for instance, with lab experiments, and which move us forward. And so in order to have this kind of comparison, it seems like we need to do it in single codes. And so Mark has a framework for doing just such a thing for two-phase. And there are some other things that Dave mentioned that have pieces of this. I think this is very important. I'm going to show you why I think it's important by comparing things and showing you what you might learn. So I'm going to talk mostly about nonlinear solvers. So with regard to nonlinear solvers, I think the first point is that we can construct nonlinear solvers that are more robust than Newton. I think there's, I know when I was in grad school and then Newton failed, it was pretty much of a throw your hands up. Lots of people say, well, what I do is I go back, I run Picard for a little while, then I try the Newton again. That's a decent way to proceed, but you can put that on a sounder theoretical footing, which we'll try to do. We can also construct nonlinear solvers that are more rapidly convergent than Newton. And this sounds kind of counterintuitive, because, you know, what do you mean by more rapidly convergent? So what you usually mean is that you have an asymptotic exponent of 2 for Newton, and you cannot improve on that, at least not with only using first derivative information, right? But you can accelerate the onset of quadratic convergence. And so I'm going to show you things that do that. Now, I have a theory that it tries to explain why this is true, but I don't know if we'll make it there. Yeah, probably not. I think Picard is never really acceptable as a solver. Now, what does it mean to say that it is unacceptable? It doesn't mean that it doesn't work. It works, it does, and it's a theoretical workhorse. However, I would ask you a related question. Is it okay to solve the Laplacian with Jacobi? That works too. It's very robust. It's just very, very slow. And it is non-uniform in H, or non-uniform in the size of the problem. So it keeps getting more and more expensive. Now, you can certainly solve your problem that way. I would say it's not acceptable for people doing science because we have plenty of experience that says we can do better. We can do multigrid, which is just doing Jacobi on a few different meshes. So by saying I think Picard is not acceptable, what I mean is I think there's plenty of experience that says that combinations of Picard and more rapidly convergent things are just as robust and don't suffer from this very, very slow convergence through the entire iteration. Okay, so you got to have a problem in order to demonstrate these things. So I'm just going to use a very, very simple two-phase example that's only mechanical, right? So no melting, nothing like that going on. Very simple closures, the simplest you can imagine. But it's, you know, it's fairly nonlinear, right? So here's the dimensionless form. This is exactly what's in Rich's paper. Okay, so it's a DAE because here are the conservation of momentum and the conservation of mass, and they're elliptic. And here is the porosity advection, and it's purely hyperbolic. Okay? And we'll just do a test problem where I have a periodic boundary and I shear it, which is I grab two ends of a cylinder and I turn. And this is neat because you can validate it, one, where there's no feedback and everything just rotates, or you can turn on the feedback and then you can do linear analysis and get this compaction coefficient. And so here's what I mean. That's what I'm doing. I'm turning it. And this is just so that we can get something to experiment with. It's a good problem to experiment with in the nonlinear solvers because you have localization and your nonlinear condition number, which is really the condition number, the Jacobian at the solution, gets larger and larger as you evolve this thing. Okay? Yeah.
Just the geometry, are you using a 2D problem or a 3D?
Oh, I just plot it like this. So this is a map. So it's a square, and the ends are identified. So that is a cylinder, and I just map it into these coordinates because, you know, they don't have periodicity in pair view. So what do you want to do, right?
You can't just view a flat thing.
No, you can't view a flat thing because I don't actually have duplicate edges of the mesh. It is topologically a cylinder,
All right.
but it's geometrically a flat plane with identified ends. That's the right way to do it, I contend. It's just the people that do visualization are way behind. They don't understand topology. So what will we do? We will start off and say, I didn't want to talk about discretization up front, so I'll just tell you quickly that this is the discretization that Dave was using. It's continuous Galerkin, okay? But it's also continuous Galerkin for this part, the advection, which people do. In fact, the paper that Dave cited about magma dynamics that just came out does exactly this. So this is semi-acceptable, at least as far as reviewers are concerned. And it's stable, right, because it's backwards Euler. So how might you go about solving this? So you can, the whole thing, you could solve the whole system here self-consistently, so there's no need to lag. You could. Okay, this is a major division in the way I think that the physics community and the numerics community thinks about solvers. So I should just go over it right now because I'm going to say it 4 or 5 times. There's a big difference between approximations of the physical problem and preconditioning. And here's a chance to say what I mean. So here I have a set of coupled nonlinear equations, and it's even a DAE in that only some are time dependent. But it's a fully coupled formulation. I am just going to solve the full problem. Now, you might say, well, I'm having trouble solving the full problem, so what I'll do is I'll solve the piece that's not time dependent, and then I'll take a step on the time dependent piece. There is a truncation error associated with this, and the way you usually analyze that is you say, oh, I have this piece proportional to delta t or delta t squared that, you know, I'm neglecting, and I don't know what the coefficient is, but I don't care because I'll make delta t as small as I need to. That's the analysis. Okay, that is a way of thinking about it where what you've done is you said my true physics is now being approximated to order delta t squared, let's say. Now, instead of that, you could take the point of view that what I will do is I will do the exact same method. Solve this, then solve that. But I will then stick my answer back in and keep doing this on the same time step until these are self-consistent. Then I don't have the same truncation problem, right? I have just the original truncation error from taking a time step at all. And my coefficients are completely different. And this is a big deal. So then what you say is this method was a preconditioner for the larger method on the fully coupled nonlinear problem. And this is how numericist thinks. So you don't say I approximate my linear problem by a simpler linear problem and just solve it. You say I solve a simpler linear problem, but I iterate on my full linear problem and I solve that to whatever accuracy I need. And this, I think, is a very important distinction. So how am I going to solve it? Well, I'm going to do Newton, of course, because I already said that Picard is unacceptable. So we do Newton, and usually do Newton-Krylov with a line search. It turns out that mathematically, Newton-Krylov with a line search is equivalent to composing Newton-Krylov with a nonlinear Richardson update, or successive substitutions, however you'd like to say that, where you just take the function composed with itself. So that's how I usually like to write it, but I'll just say those two are equivalent. And for the linearized part of Newton, I will say do what Dave did, which is in this paper by Sander and Garth and Andy and Rich in CISC in 2015. Oops, gone the wrong way. So then Dave said these things. He said, well, we can separate this into a Stokes-like part and another part, and he ignored the other part. So I won't ignore it. What it is time stepping, advection, there's the coupling to velocity, and then here's the part that Dave talked about, which I just write simply as there's a velocity part combined with the pressure part, and here the combination is sure complement, but you could have other kinds of combinations, right? And this is just a shorthand. And then I do it like this. So let me explain why you would put that on a slide. The message is the following. When you do these things, Dave showed I have a 2-field formulation, I have a 3-field formulation, I have a 4-field formulation, right? And he wrote different code for all those, and coded up a different solver for all those. And if you want to test things like this, I'm going to show you like 8 different solvers that we're going to compare to each other. Now you could write 8 codes, and a lot of people do. I think that's a huge waste of your time, and it makes it a maintenance burden, and it doesn't facilitate the kind of comparisons that we want to do. So what you really want to do is you write one code that should be capable of doing all these things, and the capability should not come from saying case 1, do this, case 2, do this. It should have a simple framework made out of pieces that fit together, okay? So here are pieces that fit together. I say, well, I want to do a preconditioner. Oh, it's a block preconditioner. It splits up the fields. Take field 0 and 1, put them in a block. Take field 2, put it in a block. Combine them multiplicatively. Look at the 0 block. Again, split it up. Combine them with a sure complement rather than multiplicatively. Do a preconditioner, which is just made out of B transpose A inverse diagonal B, like Dave said. Do a full factorization, although he was doing upper. You could just put upper there to get what Dave did. For the first block in velocity, do LU. For the second block, do algebraic multigrid. That's what Dave was doing. And then for the block all the way down here, the porosity here, it says pressure, but it should say porosity. Just do a simple iteration, right? Because it's very well conditioned. This is one way to do things. I could have coded this up. Then I would have had none of these long options. I could have just said run, right? Well, what if I want to do this? What if I want to take the porosity and shove it in the same block with A and then do a sure complement with the pressure? This is a perfectly acceptable numerical thing to do. It sounds somewhat odd physically, but it turns out to work better, and it took fewer iterates. And how does it work? Well, I just change around the way that I indicated these. Now I say take field 0 and 2 and put them in the first block. Take field 1 and put it in the last block. Okay, and it's easy to do this stuff. And there is no sophisticated code inside. The code inside is very general. It just says take this piece of the vector, take that piece of the matrix, and the pieces are identified with real physical fields, instead of, being, every row from 1 to 19 or something like that. But it's very simple to build up these things. And if you can't do this, you will spend a lot of time rewriting and rewriting and rewriting and try to figure out, whereas like in a few minutes you can test a bunch of these things and see which one actually works. And this really facilitates reading the literature too. I think there's a tendency of people not to read the literature for these problems, because I'll tell you that the first paper on these Stokes problems is not the one from 2015 that I just cited, right? It's like the work is 30 years old. And all you have to do is look at the paper, and they give you a very concrete prescription. Just do this in a block sense, and people have not been doing it because it's not terribly easy to do if you have to rewrite your code and divide things up and stuff. So we can take a look at the convergence, and just like the guys say, the linear convergence is great, no problem. And the nonlinear convergence is pretty great too, and that's quadratic. So that's what Newton does. It doubles the number of significant figures every iterate. And if you keep advancing in time, so I went forward farther, the convergence gets a little worse. So this is the characteristic of Newton. Newton initially converges linearly, and then it only later becomes quadratic. And so you can see that if you have a non-asymptotic theory for convergence, you might accelerate the onset of quadratic convergence, and this is what is really meant by improving Newton. But it's a very difficult thing to get a hold of theoretically, since all of the theory for Newton till 1970 at least was done in an asymptotic regime, and I don't know a single textbook that operates outside the asymptotic regime anyway. So that's what we want to kind of get at. And if you run it long enough, like one more step, everything goes to pot. So you say, look, what do I do? So if this happened to you, what would you do? You might say, I didn't really care about those shear bands anyway. They're already pretty converged. Or you might say, I need to put some more diffusion in my formulation, so they don't do that. But you might say, maybe I should do Picard for a while. That's an acceptable thing. I would say maybe you should compose Picard with Newton, seeing as you think Picard's producing information, Newton's not, and it actually is. And so let me briefly show you a strategy for composing nonlinear iterations, just a framework. Let me note that people have been doing these kind of compositions at least since 1970. Rose had a paper in 1970. In fact, if you kind of count Don Anderson in 1964, you can go even farther back. But it hasn't become part of the repertoire of people's solution methods because there was no supporting framework in the same way that the linear guys were able to formalize what does it mean to precondition. So Dave wrote these things down. So suppose I have an equation like this that's nonlinear. He wrote down the linear version, which looks like this, and said, this is my residual. Well, that's going to be the same thing as my nonlinear residual is right here, okay? And so he said, when we precondition, what we do is we multiply the residual by this preconditioner matrix P, and that's what he showed over here, except he showed the defect correction form, and that's what he called Richardson update, right? And it's right here. So this is what everything in iterative methods rests on. Every iterative method is a defect correction method. And when you want to do preconditioning, you do this for defect correction. So suppose we have a linear iteration. We can do additive combination. We can say, well, we'll use this preconditioner and that guy. Now, in a nonlinear sense, what you might do is say, here's the nonlinear residual, and here's the nonlinear residual with two different nonlinear methods, N and M. So this would be the analog of an additive combination of nonlinear solvers, whereas you have an additive combination of linear solvers there. And this is, for instance, how domain decomposition works. This would be one part of the domain, this would be another part of the domain. Now, in the linear case, what we say is, oh, well, what I'm going to do is I'm going to redefine my residual as that guy. Well, in the nonlinear case, I can additively combine, but it's not the same as linear because in the linear case, when I additively combined, I sort of go to first order here. So if I wanted to kind of do the thoroughgoing combination, what I might do is say, why don't we redefine the residual itself, which would be f minus b. What if f minus b is actually equal to this new thing? Okay? If we define it that way, then you have combined them where it's only first order equivalent to the additive, and it's actually a little stronger. And so what we call this is nonlinear left preconditioning when I make this replacement. And you can do the same thing with a multiplicative combination. So I don't know if this is the most familiar form for you guys, but if you see it this way, first do one thing, then do another thing, instead of doing them at the same time, right? So these are the same. These are the same equations, just expressed differently. And if you think of the nonlinear analog, what it says is first do one nonlinear solve, then do the other one where that guy left off. So that's multiplicative nonlinear combination. And you can again relate it to the linear case. In the linear case, the analog of multiplicative combination is right preconditioning, in that you can imagine changing the basis that you solve in and then changing back. And this is what Dave was doing for his preconditioner. It's because it measures things in the same norm instead of a preconditioned norm. In here we can do the same thing, where instead of changing our initial guess, we change the guess at every step we take for the nonlinear evaluation. And then you just have to come back at the end. So this, I think I like to think of this as the Schrodinger picture and the Heisenberg picture. In the Schrodinger picture, right, you change the wave function, so that evolves. So that's the right preconditioning, you change the basis. In the Heisenberg picture, you change the operator, and so that's left preconditioning. So here's a table of what I told you. These are simple ways to combine the effect of two solvers, depending on whether you want to change the basis, this one, or change the operator that you're trying to solve. And we lay them all out in this paper, which came out this year, or just last year. I guess this should be maybe 2016. I think it just came out in January. So let's try it, right? So what if we did something like this? So here's what we were using, line search Newton. And let's say line search nonlinear conjugate gradient. So nonlinear conjugate gradient does not work for this problem. I could show you the slide, but I will tell you it doesn't work at all, and neither does Newton. So neither of them really work. However, I can combine them, and it's pretty easy. I just say, let's do a composition, let's make it multiplicative, do these two guys, here's a new one, and then I use all of the options that I had before. So it's not a big perturbation for me to try this other thing out. And surprisingly, it diverges for a little while, and then it works. So, and this was a thing that did not work at all. So two non-working things, when combined, actually generate a working thing. There should be a little angel on this slide, because I will tell you that nonlinear CG almost never helps like this. But it did work in this instance. And this is what is so annoying, and this is why I'm showing you, it is impossible to a priori predict which one of these things is going to work. Yes?
You're applying this to the time step that had failed before?
Yeah.
Or to an earlier?
No, to the one that failed before, 6-4. Yeah. And so we would really love better theory, but we don't have it. And so we need experimentation. In order to do experimentation, we need the ability to be flexible. Yeah. And not only that, the idea that there is a best solver for your problem is kind of an ill-posed idea, because the best solver depends on the equation, it depends on the boundary conditions, it depends on the developed flow regime that you're in, and it depends on the architecture, and it depends on the discretization. So with all those different variables, if anything changes, probably what works is going to change, and you're going to need the ability to be flexible. So I think this, as I said, is kind of a fluke. It works, but it's really easy. And so if it works, just go for it, right? And it introduces very, very little overhead. Now, there's a better way to do things. What is the full approximation scheme? It is just not the nonlinear multigrid analog. You solve a nonlinear problem on several grids. It's not continuation in the grid, because you feed back information from the fine grid to the coarse grid instead of just going up. That's the difference. And so I'm just going to take something that didn't work, Newton, on both the coarse grid and the fine grid, and you can have any number of grids if you want, and see if I can get it to work here. And so what I do is I say, to give me FAS, and I don't need to explain the other options, do 4 levels. And I repeat all the options I had for each level. I guess I could have told it do everything. And it is very, very fast, and it has no problem converging quite quickly, even with a non-convergent Newton. Yeah, you can see it just doesn't really work to start out at the beginning, but on the coarser grids, it's able to converge. So we can try then other things, like what if we use nonlinear Gauss-Seidel, which is a lot cheaper than Newton, mostly for memory bandwidth reasons. And it's easy to try out. We just say, whoop, only on the top level do nonlinear Gauss-Seidel, everywhere else do Newton. And that spectacularly fails. That doesn't work at all. And so lots of this will not work. And that's also, it's a mistake when people do these demonstrations and they only show you everything that works. It will not work, and you will not know exactly why. I'm not sure why nonlinear Gauss-Seidel is so hopeless. It should converge okay, just slowly, but it doesn't. And it's probably because we should be doing some kind of small block nonlinear Gauss-Seidel where you solve a lot of little coupled problems over the domain. Like this would be nonlinear additive Schwartz or something like that with tiny blocks. That would probably work. This is just solving a pointwise nonlinear Gauss-Seidel. But these are all things that you could possibly try and play around, and this is only a thing that would try and make it go faster. And so that's another point, is that there are a lot of options here, and it's hard a priori to decide what will work. You have some guesses. I can sit up here and hand wave all you want about what might work, but you have to see. So I did that for FEM, and I was pretty happy with myself, and I got it to work. But then it became clear that maybe a pure finite element formulation was not acceptable, and we might have to do something else. And so I was going to have to try all this stuff over again when doing finite volume for the advection. And here, for the implicit stuff does not make sense for finite volume advection, because you can't get the connectivity pattern in the Jacobian. So you could do a simple split scheme like this, which is what people tend to do, solve these guys, stick it in, step. But what I ended up doing is this, which is what I told you. Do a step, stick it back in, iterate the self-consistency. And the iteration will not be Picard, which is what people usually mean by self-consistent iteration, just doing Picard. I'm going to do Newton, because I can take the Jacobian of this stuff, and I don't have to analytically take the Jacobian. I can just do a finite difference approximation. My Jacobian approximation only has to be first order accurate and to maintain second order convergence, so I'm okay.
With respect to the porosity.
That's right. Exactly. Well, I'm actually taking the Jacobian with respect to everything, but the other things are linear, so it's, it converges very early. So I can do it. Here are the other options. The reason I show you the options is not so that you can memorize them or understand them, but it is so that if you want to look back and say, how is he actually doing this, you can see. And furthermore, that you can see that it's actually doable. Because I really, really never believe anyone's computational talks if I can't run it myself. This is all able to be run by you. You can download it. You can use the options I'm telling you, and you can run it. And if they don't work, you can mail me and complain. And when people do these things where they do their computations in their own code, I mean, I don't believe them. Any more than you would believe someone if they told you the answer to a proof and didn't show you the proof. They're like, believe me, it's right. And I might, but, so, in order to get the Jacobian, all I do is this stuff. I say, do finite differences for the Jacobian, use coloring to speed it up, and use the initial matrix to get the non-zero pattern to color. So if I didn't have that, I wouldn't be able to speed it up with coloring. And then do a coloring that's greedy, because this is parallel, so I can run this in parallel, and it's not symmetric. And so early on, using a finite element, finite volume thing, this stuff converges pretty well. And actually, it's a little better behaved, so it makes it all the way out to 0.825 before it starts kind of not converging again. And I just broke it down into the per field residuals, so it's just like Rich said. These are all linear, so these residuals are fine, V and P. It's phi that we're really iterating on here. And so I can do FAS again instead of just Newton. And the course level, oh yeah.
I guess I didn't understand that.
Yeah.
I thought you were going to be doing one solve of the elliptic part and then the hyperbolic part and iterating.
Yeah.
Are you?
That's the preconditioner. So it's a SNES for the whole thing,
Okay.
and then the preconditioner is do one part, do the other part.
Okay.
And so that's what these options mean. And then you combine that, do one part, the other part on each level, and the way you combined it is you do restriction, nonlinear solve, and then you have the deficit, which is sort of the coarse residual with the restricted fine solution minus the restricted fine residual, and that's sort of a forcing term, and that makes it more accurate than just grid continuation. So that's what's happening here. So there's a lot of levels. So that's why I almost don't like to draw pictures of these because they're so complicated, you know, but in pieces, the outermost pieces, there's a global nonlinear solve that includes the time step. And then inside that, it's, well, I break it into two pieces. Inside that is I break it into levels, and then inside each level, I break it into two pieces, the elliptic and the fourth step, and then the whole thing goes to consistency. And so I can do FAS like this, the same as I did before. And one thing here is that the course problems are too coarse. And so the finite volume approximation is not very good this course, and they won't get to a good discrete solution. But I don't care. It doesn't have to be very accurate. So I just say, allow Newton to fail on the coarse grid. Just take whatever step it says. And in fact, it's also rank deficient. And so I just say, don't care, it's coarse, do SVD. And so what this shows is a real advantage of doing scalable methods. If you do methods that are designed to run on one scale, like the fine scale, what you get is a very boutique kind of numerical methods. It's like dollhouses. You know, you build them very carefully for one problem, and you have to do everything right or it falls apart because everything's so big that if you do anything that's expensive, you can't do it. But if you do things that are broken up into scales, here I can do absurdly expensive stuff like SVDs and, you know, steps that don't go anywhere for the most part. And it doesn't matter as long as I make a little progress in the coarse grid. The coarse grid here is hundreds of times smaller than the fine grid. So I don't have to care, and then the fine grid stuff is just polishing, and I can use pretty simple stuff for that. So this, I think, is a much better design paradigm than trying to do one level. And it has no problem again. So you can then here try to say, well, maybe at the top I will make it cheaper by going to nonlinear Gauss-Seidel with some line search. And that actually works to some extent. Yes?
Why not just use a direct solver on a coarse grid?
Oh, because I am kind of using a direct solver. It's that I could use a full direct solver, but it's faster to use a direct solver on the pieces of the blocks and put them together than to use a direct solver on the whole thing because it's so sparse. But you could. Yeah, there are some optimizations I guess I'm willing to make and some where I'm like, so that was, so I guess I should wrap up. So for nonlinear solvers, being able to, one, compose different nonlinear solvers together, even simple combinations like additive is very valuable and can get you out of situations where you get non-convergence. 2, being able to solve on different levels to do FAS is very valuable and is the best way to accelerate Newton that I have seen. However, all of these solves are tied up with how you do the discretization. And the problem is that there's a real wealth of theory about discretizations, but not too much of it is oriented towards informing the user about making a computational decision. It's almost like most people at a car dealership would be combustion specialists, and they would tell you like how well it was burning the gas, but they couldn't tell you exactly which one was right for you when you went to pick it out. So I will try to help a little bit by saying there should be rules of thumb when you pick stuff out that aren't discussed, as far as I know, in the literature. So one is, can't you just pick the right discretization? Usually, no. As I said, there's a lot of factors in which the right one might depend, like including not just what the equations are, but what part of the physics do you care about? Maybe you don't care about the part of the physics even if it's there. So the thing I was asking Rich today was, suppose we have as a benchmark the shear band problem. So we shear the thing, bands appear. Okay, do bands appear with an incredibly diffusive advection scheme? Yes, they do. If you have the right exponent, they're slanted right. They're not the same size. They might not have the same run-up. Does that matter? They might talk to each other over distances. So if you have like one of these tree scenarios, it might be a different kind of tree. Does that matter? It's not clear, right? And I don't think any amount of theory is going to get you out of that. So it's essential to run them and compare. So can you use continuous Galerkin for everything? It's a great idea for elliptic equations. So mass and momentum conservation, awesome. It's, I think, bad for porosity advection because it's very diffusive. It's not clear how bad. It's not clear what that bad means, but I think it is. And if you were doing like if you just try to uniformly advect a porous block, if you have a little increase in porosity and you just advect that thing, it's going to smear out and only in a few steps and over the size of a few cells. So I mean, it's not a small effect. And for instance, even the solitary wave benchmark that Mark showed does not really test this because you can rig up the boundary conditions to make the wave sit still in the middle of the domain, and so it never really fuzzes out. If you would force someone to sort of make it through the circle like you do in your other problems, and if that got into the publication, you ought to. Maybe the reviewers should take a look at this, and then you would have a better test. And so the shear band benchmark, as I said, doesn't really test this either, but could maybe if you did things like how wide are the bands, what kind of fall off do you have at the edge of the bands, more subtle things. But do we know that matters physically? I don't know. Well, what about just using discontinuous Galerkin? This is often proposed as the magic bullet, like, oh, CG, that's old and tired, maybe I will use DG. That's a very good idea for advection. I think it's a bad idea for conservation of mass and momentum. So forcing continuity from a discontinuous thing just looks like penalization. Penalization makes things ill-conditioned, which makes it hard to solve for iterative methods, and this results in sad Dave. This is bad for him. And so it's also a bad idea for efficiency, and you can see this in the paper by Boris and Anton that just came out. So even if you don't have that much ill conditioning, it still has a higher cost for equivalent accuracy for the same problems. Again, Dave is sad. So I would say it's great for the advection part, and it's not so great for the continuity part. So what you really want to be able to do is have CG and DG together in this thing. And you can be high order, although you do need a limiter to prevent oscillation. Finite volume also makes some sense. It handles the same sharp fronts. Going higher order there or going implicit is very difficult and just not really worth it. So in that sense, you're trading off something, although the finite volume per, the accuracy for cost is a lot better than DG. Unless you go, see the problem is that then you will read a paper by one of the DG people that says MAT is insane, DG has spectral convergence, and so it's obvious that the thing has a great cost per digit of accuracy for smooth solutions. And if you're not smooth, then you don't go to that asymptotic thing that they're talking about, right? You're at the beginning, you're at P1 or P2, and then it's not clear at all. They're very expensive compared to equivalent methods down at that order. And if you have sharp jumps, that's what order you're at. That was another point that Dave made. Yeah.
You say on the previous slide, for finite volume, the implicit formulation does not make sense. But is that what you were doing?
I was doing IMEX. I was doing implicit for the constraints and explicit step for the, I can. Okay, so here, so this is an explicit step because phi k.
Okay.
Yeah, and a phi k here. So that's an explicit step, yeah. But these are phi k plus 1, so I'm forcing the constraints to hold at the end of the step so that we're all consistent. Oh, I've gone too far. Okay, so can you do this mixing discretizations? And it turns out everyone can do it. Phoenix can do it, Firedrake can do it, Terra Firma can do it, Deal can do it, Aspect can do it, Petsy can do it to some extent. I can't do DG, so I'm kind of like sad in that sense. But so, we should be doing these things. And I was just going to show, again, there's ways to do it with options, not surprising, right? And this is the same kind of thought process you have to go through when you're thinking, should we be able to do AMR too, right? So should you do AMR? Well, from a theoretical perspective, not really, right? Because the uniform thing is completely scalable. Just run a bigger problem, right? Refine. And you might say, well, I have a given machine that I have to run on, and so I have fixed resources and I'd like higher accuracy. Well, that's a legitimate argument. Again, it's another one of these arguments where the asymptotic conclusion is not borne out with the finite resources we have. And same thing for less memory for fixed accuracy. Although AMR can affect the nonlinear conditioning in unpredictable ways. So this is a little bit of a problem. And I haven't done enough tests yet, so I don't know what's going to happen. It also complicates multi-level solves because it's not easy to understand if you're coarsening fast enough to get an overall ON out of your system. And however, you should be trying it because lots of these packages can do it. I can do it. So what are the conclusions? I think the conclusion is we need composable, extensible systems. And the reason we need them is so we can do tests and we can make informed computational decisions when you're solving these things. And you need to match the numerics to the physics. And you can only do this, I think, by a combination of analysis, literature search, and trial and error. And that's what I think we can do. I don't think we're going to, I just won't put the proof stuff up because I don't think anyone cares about that stuff. So we get to end early for the last thing. So I think that's it.
Questions for Matt then?
Yes.
I have a stupid anecdote about Newton that I don't know if it means anything or not. But
Newton the method or Newton the man?
Newton the Institute.
I wouldn't insult the institute. But so this was a problem where the unknowns are the position of nodes in a spring lattice. And sometimes, it's a quasi-static problem, but the springs can break. So the configuration is changing, but there's no time dependence, and you can't make a smaller time step.
Right.
So sometimes, it just Newton doesn't converge, and you know that there should be a solution because it's clearly a well-posed problem. So in those cases, instead of changing the solver, I would create a random perturbation to every node, a small random perturbation, maybe a few percent of where its position is, and in a large percentage of the cases, Newton then converged after restarting.
Yeah.
I mean,
So
does that make any sense?
it does because, okay, for two reasons. One is it's easy to give a theoretical answer, and that is that all the Newton theory is concerned with convergence in a ball, but you know that the convergence basis of Newton is a fractal,
Yeah.
and so it doesn't say, the convergence theory doesn't say anything about the edges, and small perturbations along the edge of the convergence region can result in convergence or non-convergence. We know that. So if you're on the edge, this just little variation can make a difference. And the other thing is that there's a more sophisticated answer which may or may not be true, which is that we know that Dan Spielman and Shenghua Tang proved that for high-dimensional polytopes, random projections are well-conditioned, which they used to do the smooth complexity to say that under perturbations, stuff like linear programming, which is basically Newton solve on that constraint problem, is well conditioned. And so there's lots of places where small perturbations actually put you in a better area. Now, I will say practically, what you can do is you can take a Newton, and probably Newton was not converging because the directions were a little noisy, because you were deleting stuff and putting stuff in. And it could also happen like if you move into other parts of your phase diagram right at the wrong moment, you're like, all of a sudden Newton thinks you should go backwards. Now we can put things around the outside like nonlinear GM-res, and what that will do is this is right preconditioning, okay? Newton will generate a set of directions, like 3 or 4, and it'll say, okay, these should improve the solution. Nonlinear GM-res takes that set, solves a small constrained nonlinear least squares problem, picks the best one out, then we go forward. So it looks like it is iterating in a different subspace. It's the space produced by the Newton iterates, which should be better conditioned than the original. And so that's the idea also of linear GM-res, but the convergence theory is totally different.
Is it a bad idea to do this anytime Newton fails to converge?
I would do this first, but that type of thinking is not wrong, you know. Especially if it's sometimes it converges, sometimes it doesn't. If it always just blows up, you know, it's not going to work.
So you have this iteration because you have time. If my phi is time independent, I will introduce artificial time, or what you will do?
Well, I mean, let's see. So if your phi is time independent, you just have a set of nonlinear equations. You don't have like a DAE. So I would just solve that set of nonlinear equations with Newton. Now, why would you put in an artificial time? Usually why people put in an artificial time is because they have a bad linear solver. Because what happens? So you take the Jacobian of this thing, and if Newton's going to converge, you invert that, and it gives you a good answer. If you have trouble inverting it, one thing that makes it nicer is I add some scaled identity to it, and makes it diagonally dominant, and stationary iterations work, right? So pseudo-time looks great for things where stationary iterations are being used and they weren't working before. Now, it's not the only reason to do it, but that's a lot of times that's why people are doing it. Yeah.
I mean, can you use the condition number of the different blocks to inform, is there any correlation between how conditioned things are and what solvers try first?
Okay, there is, however, we just have no good way of calculating a condition number, right? They can't even decide what a condition number means, because in a linear problem, the condition number is clear. Dave wrote it down. It's like, it's this guy, right? And, oh,
I know that.
Yeah. And that's fine, but the problem is that in a nonlinear problem, you could define it as the max of this over the region, right? Or where these are Jacobians, and the Jacobian depends on the point in which you linearize. Or you could define it as the Jacobian along some kind of fiber. That's how Smale defines it, which is not in a region, but it's kind of, it's the distance to the nearest singular set. The singular set's like a manifold, so he needs to measure distance to it in a weird way, right? So there's no good way to calculate these things. And there's not even good proxies. So the best proxy you have is just look at the iteration. So what you can do is try something, and if it's not going fast, change it. But we don't have any other measurements to inform the guess, really. And this is not without precedent. So what do people do in multigrid? Well, they run the smoother a few iterations and then say, is the smoother converging or not? And if it's not, then we have to maybe up the order of the prolongation, or maybe we have to run a heavier weight smoother or something like that. But they don't do anything else to the operator to try to get the analytics out. They just look at the convergence of the smoother or the match between the coarse and fine problem. Like, that's compatible relaxation, but it's the same idea.
Boris?
So FAS is not something that people, and at least in our community, have been using a lot before.
That's
I'm
right.
just wondering, in terms of implementation, like, do we only have to provide restriction interpolation operators for this?
No, there's one more thing, and I still would like to get my explanation of this better, but I'll just tell you first what it is mechanically. You need restriction and prolongation, so it's the same thing. You restrict, solve, restrict, solve, restrict, solve, come prolong back up and treat it like defect correction, right? Well, but you also need, because it's not a purely, because you're solving the full nonlinear problem on the coarse grid, so in the linear case, what you're solving is linear operator for the defect, right? So I don't need to know the solution. Now, you can solve the full equation. I could solve A on the coarse grid for an X for the full course B, right? And then I could just update with restrict X minus XC on the fine grid, right? But people tend not to do that. But in the nonlinear case, you have no choice. You have to solve for the full course problem with the guessing the restriction of the fine answer, right, equals B course. And so you need this guy, okay? So you might say, oh, I'll just use my same restriction matrix to restrict both the residual and the solution. But you can't, because you need different things out of them. You need the residual, the restriction for the residual, you need that to not alias, right? Because when you go up, you can't be dumping stuff into the coarse frequencies. But you need the restriction for the state to just be accurate. You don't care about aliasing, right? And so that's usually done by injection. And so what we ask you to provide is restriction, prolongation, and injection. So it's just different because you also need the state in addition to the residual.
No, can we just thank Matt once again? The astute amongst you will notice on the